We finished this one. Oh no. Okay, hold on 1 second. Pause the recording real quick. Okay. I have some good choices. I'm gonna do one of three things. We can finish the discussion of, we're talking about gaps and rings and perturbations. So we can talk about the classes of asteroids, which would just be rocks today. Or we could discuss a little bit more of the light that we're talking about. How, we just talked about the fact that surfaces of objects are going to take light and redistribute that on their surface by heating it uneven, right? The very last thing we saw on Tuesday's class was that the part of the moon that points directly at the sun in latitude is hotter than the edge. Right? That was the idea of the albedo. So we can use that now in understanding how atmospheres work. So we could just directly go into atmospheres and starting with the giant planets, and then begin to understand a little bit more about the atmospheres of the terrestrial bodies and how atmospheres actually work. So you have a preference for atmospheres? Recount. It's too close. 66%. Okay. Do you want to start? Do you want to start with the thermal structure of atmospheres, or do you want to start with fun atmospheres? Okay, it's going to be harder. Okay. Okay. All right. So let's see whether or not this is we're gonna wing it here. Okay. Why is it? Why is it? Why is it cold matter? That creates structure. What about it being cold means that it can have nothing? Condensation. Right? So the atmosphere can be fully understood in its formation. Not fully, but 80% of the information that you care about. 80% of everything that you care about in the formation of the solar system is understood with a graphic like this. Okay? It's hot in the sun. It's colder away from the sun. And then you just draw a couple lines. Okay? This is where water condenses. This is where methane condenses. Okay. So you're going to get methane into a planet body, then it has to be cold enough that carbon can grab these beaches and become solid. If it's a gas, then it'll just be broken apart flat. So the color you see here, purple, the blue, that's all methane. You have storms. We'll talk about the atmospheric storms there. And we'll talk about how you get atmospheric dynamics at all. Okay. In order to do that, we have to start with something like hydrostatic equilibrium. We'll talk about what happens when object is out of hydrostatic equilibrium. Talk about the process of adiabatic expansion, cooling. We'll talk about convection zones. So in the atmosphere itself, what does that mean? And then hopefully we'll get to understanding these temperature profiles. They're going to start with our understanding of the Planck function, right? The emissivity as a function of latitude. And then you add on to the fact that once you start heating a fluid, it can redistribute that temperature. Okay. And then we'll end by discussing how molecules escape and what that leads to when you think about terrestrial systems. We'll start with just the biggest ideas, and then we'll look at individual things. Okay, so you are familiar with the ideal gas law? What is that? EV equals nRT. And what is what? Pressure. I'm not going to write it. Volume. What? Number of moles is not a thing. Moles is a unit. Right? But I wouldn't say like number of kilograms. I would say what is the thing, right? So this is the number of atoms or molecules. Good. What's this? Good. Yeah. And this is there. All right. You're experts in that, right? Good. You won't need it. Okay. You're not learning that. You're children. You're men. Sorry that you're not here, but whatever. Maybe you're not. I don't know how you said bye. All right, let's go. Come on. All right. So why do clouds? Oh, wait, hold on. This is the wrong part of the wrong lecture. Fuck my life. Hold on. We're gonna start halfway through the other lecture. You want to learn what? Oh, we're going to. But you just have to first learn what they are. Okay. Let me just. Here's where we're going to start. And let me plug this back in. First thing, we're going to start with the idea of clouds. Okay, we just saw those clouds on what's the name of that planet? Neptune. So let's talk about them as a concept, and then from there we can look at how they are created. You know, we need a little motivation in life sometimes. So what are clouds? Right. They're a form of condensation that's entrained in a fluid. Right. So it's not like aerosols. Aerosols don't condense. They don't go back to a gas form. Dust do not condense. So this is a different phase. Right. So Earth has water ice clouds and water clouds. Those are different. Mars has CO2 ice clouds as well as water ice clouds. Venus has liquid hydrogen sulfide clouds. You're fucking sick. And of course, the giant clouds either have ammonia or ammonia hydrosulfide. or nothing. They have water too, that's the white. Right. That's a real cloud. What are the three things you need to make a cloud? Heat. Make a cloud?
Well, unless you're talking about its composition.
No, how do you, let's say you're going home tonight, and you need to make a cloud for your grandson. Alright, you got a recipe at home. For what? What do you need pressure? You need pressure, like, you have to be in an atmosphere, I agree. But is there a specific, can you add more words to that? Okay, like, what does your recipe call for?
It's more primary than water, right? Correct.
Yeah, let's say you wanna make a waterized cloud at home. Use evaporation. Okay, now you're thinking too many steps. There's nothing like how to make one in the atmosphere. I'm saying, what three things do you need at home? You need water, that counts as one. You need it to be cold. And you need something for it to crystallize. Condensation does not happen spontaneously. So in fact, on the Earth, most of the condensation occurs as there is dust, haze, and so particles can condense onto it. There's no such thing as spontaneous condensation. Now, interestingly enough, once you have ice particles, it's very easy to continue to condense on them. Have you ever seen the shape of a star flake? Yeah, snowflake. Shape of a snowflake, right, is because you start in the middle with something, then you build around it ice. Okay. That's condensation. Let's have a look at some more pictures of clouds really quickly, and then we'll talk about the science. So on Jupiter, and we'll see this when we go back and look at this more, there are various places on the planet with different colors. And in this image that you see here, this also has different velocities. What that means is that some parts of the atmosphere are going in opposite directions to the others. And you might be saying to yourself, how is that possible, right? The entire thing is spinning, right? Shouldn't it all be rotating together? Well, one of the issues with a rotating fluid is that it will rotate differentially. So for example, near the equator, it is rotating faster. Right? So necessarily, if it's rotating faster here, it's gonna pile up against something else, or it's gonna be shear. And in fact, we get jets that form where you have oppositely directed fluid. And we can see that in the vertical structure. So that's why there's bands on Jupiter. And in the clouds themselves, we have different colors. So at the very top, you have ammonia. That's the bright white in the upper. You have water. That's the lower dull white. And then in the middle, you have the hydrogen, the ammonia hydrosulfide. Okay. And that's in the middle. And that's what gives it its, brown, very deep. So the simple thing that we want to remember here is that wet air rises and dry air sinks. That. Yeah. Think about it this way, right? Now I have a box, and that box is filled with gas, and then I add water vapor to it. Is that box heavier or lighter? So take a box, a box of gas. Take a box. Don't think about the question. Don't think about the prompt. Take a box of gas. Add water. Is it heavier or lighter than when you started? Has to be heavier, right? So moist air, by definition, is heavier than unmoist air, right? Because there's the addition of moisture, and water is heavier. Okay. So this should be counterintuitive, right? And this goes to your point that it must be hot because we expect it to be heavy. So the only way to make up for that, so our ideal gas law that we immediately believe in, right, is to lower the density, right, by making it warmer. And that's true in a lot of cases. What warm air, sorry, hot air rises. Oh, no, I keep saying this, I'm not supposed to. Wet air rises and dry air sinks. And so in a lot of ways, when we're looking at different cloud colors, we're also thinking about the humidity of the gas. And we can think about the word humidity in very different ways. Because you, of course, are familiar with the idea of water humidity, but you could say the humidity of ammonia. Right, that's perfectly fine. In fact, what you really would say is the partial pressure of ammonia, but that's not what we're going to talk about. Okay. And well, this is true. I think it's some of this is still true. I'm not quite sure what the atmospheric component is in the great red spot, but it's a storm, and it's upwelling, right? So it's drawing up material. So we think that it's starting to humid for this cloud thing for sure, but their composition is slightly. Questions about this and zonal flows? So this is kind of a structural thing. We'll talk about why the structures form when we see some of the larger structures in Earth's atmosphere. You guys know about Hadley circulation? Okay. This is an example of Hadley circulation. We'll talk about that when we see Earth's easiest to understand. Okay, they're not just declaration. They are tied to the atmosphere. They're extremely important, right? Clouds are every planetary scientist's least favorite thing because they're very pretty, very nice, but they're very highly reflective, right? So a cloud that's very high up in the atmosphere will essentially reflect more light and make the surface cooler. But they also are opaque at infrared wavelengths. So if you put that same cloud close to the surface, now you're trapping in heat, making the surface hot. So both of these things can be true at the same time, and particularly if the planet is not fully covered in cloud, let's say partial cloud cover, this makes modeling fucking nice, right? Okay. So modelers hate clouds, and particularly when people tell you, oh, you know, we looked at this exoplanet and we think that it has this, that, and the other properties. It's like, well, what kind of atmosphere did you put? Do you model clouds there? Probably wrong if you didn't, right? Okay. Condensation and freezing, these are phase changes. You know that already. However, one thing that you want to remember is the idea of latent heat. Oh, latent heat is. What's latent heat do? Latent. What? What's latent heat? It's that it has, or it gains or gives off. Yeah. So it's really important that there isn't extra exchange. And when we think about the phase curve, and of course I'm going to draw this wrong, so just it's about the vibes, right? It's not really the numbers that I'm going to write here. So okay, let's imagine you have some frozen block of ice, and you are applying energy to it. You're applying energy, you're applying energy, you're applying energy, and maybe you're melting, or you're getting closer and closer to the melting point. By the time that you get to the melting point, it takes energy to make the phase transition, And then you can continue turning it into, say, a liquid, heating a liquid, and then by the time that you want to evaporate it, then you have another plateau, right? And these things here are your latent heats of sublimation or evaporation, right? Or condensation. And they're exchangers. So in particular, the latent heat is released into the cloud surrounding. So from the process of condensation, you get rid of heat. Right? So you notice here that I'm going in this direction, I have to add additional heat. So if I'm going this direction, for me to do this, I have to get rid of that heat. And so that's the process. This latent heat, when we think about hurricanes, right? This is the reason why hurricanes can be self-sustaining. Is that as clouds move up into the atmosphere, they're dropping heat. It's how you form storms in the first place. It's condensation. Okay. So we'll see this more when we think about storms, but this isn't maybe keep in mind. Okay. We need to talk about why clouds form at a particular height. It's a super shitty picture. Oh my god. I don't know why it came out like that. It looks like a Rembrandt painting. Okay, we're gonna fix that. I have lots of very good cloud pictures, and for some reason that is not looking good. And the thing that we want to think about is why do clouds form? So we talked about three things. We said we need nuclei, we need water, and we need to be cold. Okay. Now, can you make a cloud from a single piece? No. You need to think about clouds as vapor pressure equaling the saturation vapor pressure. What does that mean? That means that there exists an amount. Let's go back to our idea of a box. You have a box, you can put some water in it. If you put too much water into that box, it will condense out and it'll just rain. Then you have water and air separated. But if you put the right amount of water, then the water molecules will bump around, right? And they'll just be chilling. Okay? So saturation describes how full is the air of your whatever quantity it is, right? We're going to use water here, but you could, in your mind, say ammonia saturation, right? For safe time. Okay. So this will depend on the temperature and the pressure, absolutely, as we talked before, but it also depends on this idea of the partial pressure. So what this means is how much volume are you filling with your molecule, your water molecule, okay? And we'll see this in practice when we talk about this equation. Okay. So when droplets get too large, they fall, right? So you've seen rain, maybe not in California in many years, but it happens. And this process is essentially, material, this is warm, humid air, it rises. That's the warm, humid air, it's rising because it's hot. And then it gets cold enough, and it gets cold enough that the vapor pressure becomes close to the saturation pressure. And then you get droplets. And what's interestingly enough is you can have little itsy bitsy tiny droplets. This is a water vapor cloud, not a water ice cloud, right? So that means that it's liquid. You stick your hand in there, it will get wet, right? Now, of course, that's from condensation, well, for your warm body, but you get the idea. So the idea is that this thing, not fluffy, wet, moist. Okay. So then you get all of this water that's all hanging out here. And at the very bottom, let's say you have too much water, then those droplets get too large and fall. That process makes sense? Okay. So conceptually, we understand. All right, there's your phase diagrams. On the left-hand side, you have water. And the fabled triple point for water. Where the triple point is? Water. Here's this location. This is the temperature in Celsius. This is the pressure in atmospheres. So we live like here. water is liquid. Awesome. Good. That's very convenient. If we lived in a much hotter planet, it would be we call one spot.
Paper.
Steam. Yeah. On this side we call it steam. Down here we might not call it steam, right? You never one spot of cloud is steam. But the only difference is temperature, right? A little bit of temperature, but that's the difference. So you drop the temperature down. Good, and then over here you get here's one one atmosphere. So over here, when you drop it below 0.099, that's the freezing point of water. Oh, sorry, that's the triple point. Freezing point is zero. I can't tell the scale.
It's a very bad.
This should be zero. But that looks very close. I don't know if that's exactly right. Anyway, that's the point where it freezes, right? And this is where you get snow. So snow, sweat, steam, right? That's at constant pressure. As I move up into the atmosphere, I go down, right? And then let's say I'm at the very top of the atmosphere. It might be such a low pressure that I simply take a solid, right, the water ice cloud, and immediately turn it into water vapor. No drop. Right? Whereas let's say I'm more lower in the atmosphere, I might be able to get away with transitioning through the droplet stage. Okay. Let's compare to right? Carbon dioxide. So Mars, famously, carbon dioxide. And it's cold there. So it's cold there and the pressures are low. So this is 5.1 atmospheres. Right? That's higher than us. Mars is way down here. Mars is not in a world in which you would ever have liquid CO2. Where do you find liquids? What? You find it in the solar system? Okay. Oh, very interesting. Yeah, the problem with saying this is it never gets opened up. Do this. In the atmospheres of gas giants, you might be able to, but as soon as this pressure goes up, medical system. That's the answer. You find this not natural. You do not find this naturally. Okay. Because exactly like you're thinking about, right? The temperature here and the pressure here, they never agree. Because if I just compare this to any other gas, it's gonna come. Right? CO2 loves to be in a gas. So generally speaking, we find this right here. And you go down here almost like let's say one is like down here, right? It's just almost all gas all the way down. How do you get this? What? They were good. Where can I find solid CO2? This can be found solid. Yes, where? Let's do the silly answer first. Albertson. This is what? Dry ice. You can find it at Albertsons. You have to ask. It's not dry ice. Yeah, you have to ask. It's behind the counter. But they'll sell you it here. Okay. So that's CO2. Good. Where are you finding the solstice? Yeah, it's definitely cold enough in the hydrobelt, but that's not the place that I'm thinking of. It would definitely be in comets. Yeah, absolutely. And both have the same idea, right? Outer solar system. Good.
Hot chocolate. Right.
Mars's polar caps are predominantly CO2. So Mars, throughout the course of its year, the atmosphere will breathe. What that means is that as the temperature gets higher and lower, it transitions back and forth across this phase transition, and the atmosphere condenses out by about 30%. I want you to imagine what that would be like here on Earth. As you go to a place like Colorado, and people find that it's hard to breathe at a mile up, that is only a reduction of 20% in pressure. So imagine if throughout the course of the year, people at sea level seasonally found themselves losing something like 30% or like moving, like the whole population moves up to 7,000. Pretty fucked. So that's a unique property of the Martian atmosphere. Okay, you having fun? Yeah. Okay, so now let's go back to everyone's favorite clarion clapperon schmishmasher. Okay, so it's almost like I meant to do this. Here's how you make Clued. Oh God, now I can't find it. Is it down there? Thank you, sir. Okay, so let's make cloud. Here's the partial separation. Partial saturation pressure. It's the saturation partial vapor pressure at a given temperature. Okay. And this is called the Clausius-Clapeyron equation. So here is that partial saturation pressure, right? That's what this means. What is the pressure at which you start to consider condensing clouds? So this Cl, that's going to depend on the molecule itself, whether that's water vapor, whether that's a mixture of water vapor and ammonia, whether that's ammonia to hydrogen sulfide. And then up here, you have the latent heat of condensation. We talked about that. That's this, delta H. Good, and it's exponential. Okay. So in a lot of ways, the height at which clouds form can be an estimate of the temperature. In some regards, it can also be an estimate of the partial pressure of a particular gas. So if, for example, you're going home tonight and you're driving on the freeway and there's clouds, right? And they're low or they're high. Which of those two situations is it likely to be cooler at the surface? What do you say?
This is trying to. It's the close picture always goes down.
Right, so the cloud is already formed. And the location of the cloud tells us usually something about the temperature. So the location of the cloud always happens at the same temperature, right? Okay. Temperature. Oh, sorry, here's temperature. Here's altitude. We'll call it H, right? That's the hottest part of the atmosphere.
Highest part of our atmosphere. Away from the sun. It's like when people.
No one has. Yeah, we don't know about that. We just live on the surface. This is all we care about. Right? Temperatures get colder as we go up. Right? We know we go to the top of the mountain, it's cold. Right? Okay, and now I'm also saying, here's H. One day I found a cloud here. Another day I found a cloud here. Which of these two situations indicates that the surface will be colder? I said clouds are incredibly tricky, right? And that they're a pain in the ass to model. That's what you should take away from that statement. Don't make any assumptions about that. Right now, we're going to do the very simplest approach to understanding atmospheres. And just know they're fucking nightmares. Okay? They're cool. They're really, really cool. They're just hard to work with, right? They don't do what you expect them to do. So the first approximation, this is how we think the atmospheric temperature changes. Then using this with this, which of these two has a colder surface? What?
You stated that as we go up in altitude, we recognize that there's colder temperatures.
Yeah.
So the cloud that is higher will also be colder.
Right, but so let's think about this for a second. What temperature does water condense? Let's say at the surface. Right. Why is it lower?
Because the surface is colder in the atmosphere. Surface. Well, I'm having a hard time describing this, but if the surface is cold, then it doesn't need to go as high to receive the heat.
So let's think about it this way. Let's imagine that this here is 0 degrees. Okay? That looks stupid, but you know, right? Okay, so let's say that is 0 degrees on this day. If it gets colder and the whole curve moves to the right, that has the same shape, now the cloud forms. Oh. This is just using the idea of how location of the cloud can help us infer the temperature. That is not always true, and you certainly will see, and we'll talk about this thing in 2 or 3 lectures, examples of that not being true. Right? But as you move up and down, right, that same temperature might not be the same, right? Because if it's high enough, the pressure is going down, so you might be able to form temperature at higher temperatures, but form a cloud at higher. Okay, so let's make an atmosphere. How do I make this curve? Right. Here? No. So let's say, let me rephrase my question. Let's just imagine, like, we talked about like going up the hill, right? So, we have this like sense. Here's temperature and here's height, right? And we said, you know, it's hot at the surface and it gets colder. And I just drew a line. Okay. But is it like that? Is it like this? Is it like this? How do we know? Can I draw that line? Can I use physics to give me what I think that should be? It's motivation, right? Okay. So have you ever seen the derivation of hydrostatic equilibrium? Okay, let's break down some words. Hydro. Water. Close but wrong. Fluid. Because we will use this for gas. And it'd be kind of silly, right? So we're going to be talking about atmospheres. We're going to live in a water atmosphere. We're going to live in an air atmosphere. Static.
that remains the same.
right? So this is not time changing. Equilibrium. Interestingly, not what that means. Equal means it's the same. Equilibrium means wait, this is a balance. Things are being balanced here. Two things are equal. Hydrostatic balance is another way of saying this, right? Because the not changing component that Garrett's alluding to comes from the word static, right? So it's not saying water static static, it's saying water static balance, right? So what that means is that we can do the free body diagram of any particle. So imagine that this is a cube of air. Why did it fall? Gravity what? Gravity acted on it, right? Oh. All right, gravity acted on it. Let's do the free body diagram. Here's your box. How do I read it?
The air will be snow. Force of gravity.
Good. And what is that?
Then we need to get these things. Oh, no.
Don't ever use a number on me. What do you? What just letters? Just tell me letters.
Negative and energy.
Yeah, I'm gonna let the arrow here show us the. But good. That's right. That's all I want. Okay. And yet, if this was air, all the air is not falling out of the air, so to speak, and collecting on a puddle on the ground. So something must be pressing it up. Okay. The force of something. P. Okay. So in fact, gravity and pressure, air pressure, are magnets. So consider a small block. It has thickness dz. It has an area. We call that S. And the whole thing is rho density. So in this direction, I have rho g. Do we see how we go from this mg to rho g? What is m? How do I write it in terms of rho? Rho v, right? Okay, so this can be written as rho vg. And what's the v? Well, it's dz times s, right? Rho dz s g. Okay. So there's a pressure above and below, and they're not necessarily the same. Right? There's pressure pushing down, and there's pressure pushing up. So if there's a force this way, there has to be a force that way as well. So instead of using forces here, we can use pressures, and we can divide by S. The S will fall out later. You'll see that. I'm going to leave it like this for right now. See right there? That's okay. Okay. So let's move to the next part of how we derive this.
Oh, wait, let me draw this differently.
Let's do the force balance of it. Let's do we make one more statement. Here's the force. How do I write forces in terms of pressures? Are they related? What are the units of pressure? We have one, not ounce.
Centimeter cube. Centimeter cube.
That is.
That's volume, that's centimeter cubes per.
Okay, let's give you an easier one. You need to go fill up your tire. PSI, what is that? Sure is PSI. That's the unit. It's pounds per square inch. Okay, so pressures are pounds per area. Ah, so forces are pressure times area. And I can rewrite this as what? Pressure times mass. Good. Now, the thing that I have to keep in mind here is that it's a slightly different location. Remember I said that there's two different F's? So I want to be really careful. So over here I have F P at Z plus DC. And up here it's just at Z. Does that make sense? So this would be the pressure at Z plus DZ times.
Could also still be a.
Yeah, it's still S, right? That's in the top end. Cool. Okay, so let's put these all together. They have to be balanced. So let's consider ups and downs. Now they need to be equal and opposite. Okay, so what do I write? E Z times S is equal to
P times commodity. Z plus DZ. Times S.
it's not times the quantity, right? It's evaluated there, but that's okay. And
Plus. P.
I'm going to do rho G S DZ, just to put the DZ on there. Okay. All right. Now that's going to look like what I have. Help. Okay, phew. Didn't lose my job. Okay, so let's do the first thing. Let's get rid of the S. That's fucking useless. Not helpful. So we don't care about the area as long as it's the same density, right? And interestingly enough, this one here, right? This is P minus PZ plus DZ. So this is a function, and you'll remember if you took computational. What's the definition of a derivative? dx of some f,
So
right? But what's the fundamental theorem of calculus? Definition of a derivative. Yes, the limit of x. Okay, you are one part of a step there. I'm going to give you x goes to 0.
X.
What? X plus h. Okay, let me just. I'm gonna make it a little easier. Let's make it easier on everyone. Let's not use too many letters. Let's do delta x. Is that okay? That's the first part. And what else?
Plus F. Not plus F. Delta X.
Is it plus?
No, minus.
Is it?
If you divide it by.
So what does this mean? Okay, let's look at this object. Here is f of x. Here's x. Here's something. Here is the location, f of x at x. Here is the location, x plus dx. Here is f of x plus dx. What is the slope? It's rise over run, right? So that's the difference. That's rise. That's run. The rise is this one minus this one. That's how you know that the minus sign is there. The bottom one is this one minus this one. And the x is canceling, you have delta x. That is the fundamental theorem of calculus. Okay? Another one you should memorize. Understand. Really good. Bit of the brain. Okay. Do you see the fundamental theorem of calculus?
Yes.
Yeah. Because if I move this over, okay, let me clean this garbage up a little bit. No, I'm not going to. I'm going to do P of Z minus P of Z plus DZ equals rho G dz, right? Okay, okay, now what? Now what? Divide the dz out, good. Now what?
And we multiply both sides by negative.
Yeah. Yeah, let's do that. Let's do this and this. I'll put the negative over there. I'll remember that. Okay, so that means that negative rho G is what? dz of pressure. Very good. Okay, that is what we're going for. This is the statement of hydrostatic equilibrium. Okay, notice how I did that. I said that the pressure is in balance with gravity. And if you look here, that's exactly what this says, right? The rate of change of the pressure is exactly equal to gravity pulling you down. Okay, so that's what it says over here. You did a great job. In radial coordinates, we would do like with R. That's okay. We tend to do hydrostatic equilibrium just on flat plane, you know, just assuming that we're going to model like here, local. And a lot of the work that you'll see will be based on that. Okay. So the trick, and we'll see this, I don't know if we're going to see it right away. Yeah, the trick tends to come in describing that this is this a solvable equation? Is this a solvable equation? Fine. How do you know the next? Okay, so let's ask you a question. Let's ask you a question. G, we can't change, right? That's there. Rho, is that going to change? Yeah, so in an atmosphere, it changes, right? At the surface, it's lower than higher up. So necessarily the pressure's changing, right? So typically this is not solvable unless I can express one of these in terms of M. Is there any way to do that? Say for gas. Say an ideal one. I don't want numbers, right? I want to add more things to make my life harder. Make my life easier, bro. What's the ideal gas law without volume? Thing that I have. How is P related to rho? That's how it is. These, by the way, this is the ideal gas law. Anytime that I relate these two quantities, they are called equations of state. Okay? And they make solving the hydrostatic equilibrium problem possible. Right? So in fact, the hydrostatic equilibrium exists in a place that you may never even think it would exist, such as the interior of stars. Yeah. Does the ideal gas law apply there? No. But we do know how the pressure and the density relate to one another. Yeah.
The K, is that referring to the step of multiple?
Yeah. Yeah, you're gonna see that in 2 seconds. I think it's the next slide. Come on.
Yeah, there you go.
That totally gets the same K as the
There's a little bit of a see this here? So this is the mean mass of a molecule. If you have a mix of things in the atmosphere, you have to use this. If it's one gas, use that. I tend to fold it into there. You can do that later. This is all you need to know. That part. Okay. If we use this and we assume uniform temperature, then we can solve this. Right? Okay. But let's first take this gas law. I'm going to drop the mu. How can I write density in terms of pressure? So let's write the P equals rho KT. How do I write density? P over KT. Good. So now what is my hydrostatic equilibrium from that side of the board?
negative.
Negative rho G is D Z what?
Sorry, pressure.
Okay. And now I'm going to write this up here. I'm going to rewrite that as minus rho over K T times G. Right? Okay, actually, I'm gonna be a little bit more clear. Just gonna switch this one. I'm gonna put the G on the top. Like that, that's okay? And this is P. Okay, what's the solution? Nope. You should know this. You should know this. This is one of the only ones that you can look at and know the answer. Guys. Yeah, my brain is gone. Let me just show you. Let me remove some letters and it'll pop out to you like, oh, okay, ready? Ignore this. Okay, I'm gonna rewrite it. df dx equals f. What is that?
0.
No. No. Question is, what is f? What, when I take the derivative of f, I get f back. Only one thing in the whole world does this. E. There we go. See? Okay, E what? Exactly. It has to be E to the X. Good. Okay. Now I know how to do this. Right? So when I take the derivative of P with respect to Z, I get this thing out and the thing back. So that must mean that P is what? Good. E to the Z, but it needs some garbage. This garbage is going to come out, right? So where does it go? It goes in the exponent, right? So it's minus GZ over KT. Okay. Is that good? Now that's not exactly good. Why? Yeah, it's gonna come out. That's good. That's not what I'm worried about. What units does the exponential have? You know, there's KT in it. No. What units does the sign have? What? What did you say? No units. Sines and cosines have no units. Exponentials don't have units. They are numbers. So where's the units in my equation? When I do a derivative like this, I can always do, and check this out, you're gonna love this. I can just arbitrarily add something that multiplies. And in fact, that's what I'll do here. I'll multiply this whole thing by a pressure at some location. That's going to hold the units of pressure. And then this is going to give me the shape. Now I said GZ over KT, right? So there's my function. I start at some maximum pressure when Z equals where do I start at the highest pressure? Well, I'm not changing temperature at all. But that's with Z equals 0, right? Like, well, let's look at the exponential function really quickly. And particularly, I want to look not just at the exponential, I want to look at one exponential function of the minus parameter, right? So here's x, and here's f of x, okay? And I want to write e to the minus x. What does that look like? Students? Start at x equals 0. It's e to the 0. 1. So at x equals 1, I get 1. And define 1. It's defined, it's right there, right? And then as it gets larger, what happens? Goes down. Okay, so I just go like this. Right? And let's say I go infinitely far away, I'm gonna head towards, like let's say x is infinity. 0. So it never crosses into negative. Right? There's no sign change possible by the x. If I started in some kind of negative space, yeah, then I can get bigger. But here, it just gets smaller. So notice what I said. The exponential has a maximum at z equals 0, where my pressure equals whatever my constant was, and then it gets smaller. Okay. Everyone gets this? You know how to do this at home? You gotta do this at home. Okay. That's them doing the integral. See how gross that is? You can just know it. How cool does that look when you're spotting it? I know what that looks like. Thanks. Now, this is how you should do it. And when you read it home tonight, this is how you will read it. But the work that you see on the board, one of the things that's really fun about doing derivatives is you'll just start to see, you know, like when you see like the pieces in a puzzle, oh, that's exactly the piece that needs to fit here, right? There's only one piece that can fit in that puzzle piece. And so once you've memorized that it's the exponential, then you just have to learn how to turn it, right? Whether you need an a, whether you need a constant that doesn't have an x, right? And then you can figure out the rest of your problem. Cool. And this thing here is the isothermal scale height. We're going to call it H. And what that means is, I didn't draw this very good. Let's pretend like I do this thinking about the next part of my slide. Here's 1, okay? And I'm going to go out. Let's say I rewrite this. X. Oh, God. Oh, go away. Okay, let's write this x over h. Okay. So let's go out to a distance x equals h. Okay. What is my value? Almost. Almost. There, and that is what? Let's be astronomers. What is E, by the way? An astronomer, not to a mathematician. Good. So what is 1 over E? Yeah. So here I am down here at 1/3. Okay. All right. Now let's go out to 2H. It was natural, right? But it's not it.
Be the square root of 1.
Nope. Yeah, it's 1 over E times 1 over E. Right? Because if I put 2 over here,
1 over E squared.
1 over E squared, right? 1 over E squared. So this is 1 over E to the X H, right? Or 1 over E. Okay, all right. So this one over here goes to 1/9. Now, we call this length the scale height. The scale height is the height at which the atmosphere loses 1/3 of its quantity, or is reduced to 1/3, right? So if, for example, we're describing the pressure, then the scale height represents how far you move and reduce the pressure to 1/3. I'm running out of time, but oh, this is good. We're going to talk about scale heights next. We'll jump into a lot of the atmosphere stuff. Okay. This process makes sense to you? To do the derivative? Okay, you can do that at home now. All right. You can look at this one too. This will get you the same place. But if you don't like integrals like me, balance. Right? So one of the fun things about quantum mechanics too, when you get into quantum mechanics, you can guess the solution. You just look at the shape of the derivatives. Like I got 2 of these types of derivatives and 1 of these types. That means only these types of solutions are valid. So looking over here, you say I see the function on both sides. And one of them is being taken a derivative. The only thing that it could be is exponential. What if there was 2 spatial derivatives here? I'm gonna write this and I'm not going to answer it. I want you to think about it at home. Good. And you're right that that is a solution. Is it the only solution? This knowing how to find all of this. Will it help you if I do this? No, that.
Fine.
Or. Oh. So in fact, the best way to do that is that f of z is the I plus, or sorry, plus e to the minus
Is it over two?
one.
Is it over two?
No, you can just write any way you want. You're gonna, I mean, you're gonna add like, you know, a naught here and b naught here and whatever works for your function. But as soon as you see that, it's also an exponential. Like this is the beautiful connection between the exponential function and the sinusoid. Trigonometric functions for children. Exponentials. What's that?